Hey everybody, this is lecture number 9, Understanding Standard Deviation. Our EQ is how do I interpret standard deviation so that it makes sense for me? One of my biggest goals is for you guys to be able to know what this quantity means. I was all the way through college and did not understand it. The only time I started to understand this is when I taught it. So that's my goal for you, is to you guys to be able to understand it before you actually even get to college. Let's talk about it. So standard deviation is mathematically the average distance data points in a set are from the mean. That doesn't make a lot of sense. Let's go with a very, very basic at least understanding. If you have a big standard deviation, that means your data is more variable and more spread out. If you have a smaller standard deviation, that means you are less spread out. Everything's more condensed and consistent. Now, this is an interpretation that you will want to, it's like a little template for you to use, okay? What it means for you. On average, a randomly selected individual will vary by a standard deviation from the mean. You just need to fill in the blanks for individual and standard deviation. You'll see what we mean here. Now this, to me though, is the more useful way of understanding it. Unfortunately, it's not commonly accepted. I like it though. I think it makes sense for me. Typically, I can expect a randomly selected individual to be within a standard deviation from the mean. Okay? This measurement of spread is very closely tied to the mean and the typical individual. So let's try and identify what it is we're actually going for here. I have here a collection of 14-year-olds and their foot lengths of 7 randomly selected 14-year-olds. I never know why I don't change this from year to year. It's super creepy. It's super weird. I know. Just bear with me. Okay? Let's just ignore the creepiness and let's just move on. So the first thing we need to do is find the mean, because we know the mean is in the definition, right? So we need to find the mean. Adding all of these up and then dividing by 7, I'll just go ahead and cheat. I know the answer, and that is 24 centimeters is the average 14-year-old's foot length in this sample. Now, we need to see how far they vary from the mean, right? It talks about variation from the mean, or deviation from the mean. So deviation means we need to subtract. Let's take each individual and subtract it from the mean. So 20 minus 24, this individual has a deviation of -4, which means they're 4 inches or 4 centimeters shorter than the average foot length. Doing the same thing for this individual, they are 2 centimeters shorter. This person has an identical foot to the average, so that's going to be 0. And now we can start to see the pattern. That's going to be 0. 25 minus 24 is 1, 1, and then 28 minus 24 is 4. Okay? Now, what we would just say is, all right, well, let's take a look at what's the average deviation. So let's add up all of these deviations, right? If we add up all these deviations, we end up with -4 plus -2 plus 0 plus 0 plus 1 plus 1 plus 4. If you're kind of savvy here, you can start to see what's going to happen. -4's undo each other. 1 and 1 is 2, and those cancel each other out. And now what are we left with? A big fat 0. Does that mean that on average somebody has the average foot length? That kind of makes sense, right? That seems obvious, but that doesn't tell us anything, because this is going to happen in every single data set. If you add the deviations and take the average of all of that, you're going to end up with 0. So what we need to do is find a way to handle these negative to positive values. And the way we do that is we square. Because what happens when you square a negative number? It becomes positive. So let's do that for all of these, squaring each one all the way down the line. Now, let's go ahead and take the average of these squares. Okay, we start off by doing that by summing them all up. So what's 16 plus 16 is 32, plus another 4 is 36, plus another 2 is 38. So the sum of my square deviations would be 38. And now let's take the average of it. 38 divided by 7. And that gives me 5.429 and then some other repeating decimal. We might think, okay, well, that's great. That tells me that on average, a randomly selected 14-year-old's foot will vary by 5.429 centimeters from the mean. Well, hold on for just a second. Okay. If I were to add that 5.429 to 24 centimeters, I get 29.429 centimeters. Did I have anybody that was 29.429 centimeters? No. I didn't have anybody that was longer than 28. So we missed something here. What did we miss? Well, we did some very specific operation here that was very much extra, right? What did we do? We squared things. So what do we need to do? We need to unsquare them. Take the square root of 5.429. That's going to get our centimeters squared back to just centimeters. And when we take the square root of that, we're going to end up with 2.33 centimeters. And that is our standard deviation. And that starts to make sense. On average, we have individuals that will vary by 2.33 centimeters from that average. That tends to make a little bit more sense based on what we're looking at. So I can use this sentence starter, this template over here, to try and write that out. On average, a randomly selected 14-year-old will vary by 2.33 centimeters from the mean. And there's our interpretation sentence. Okay, I can highlight the things that I had to insert. Randomly selected 14-year-old will have a foot that varies by 2.33 centimeters from the mean. Everything else was just straight from that interpretation sentence starter. Okay, let's go ahead and break this down a little bit more by looking at the formula and seeing where this formula comes from. All right, so here's our formula. And it's a big, nasty, gross one, right? But let's try to read it. I want you to be able to read mathematics when you're in this course as well. Okay, so the standard deviation, S sub x, first of all, this is for a sample, because it's not sigma. This is for a sample standard deviation. Think about your order of operations. The first thing that you should do is always look inside your grouping symbols. Well, we've got a big grouping symbol here in this square root, right? And inside that square root, we have even another grouping symbol by this big capital sigma, which remember tells us to sum everything up. Well, what is it that we are going to be summing up? Go inside the next grouping symbol. X sub I minus X bar. So this is our first thing. X sub I refers to each individual, X bar refers to the mean. So here we are looking at the deviations from the mean, each individual deviation from the mean, and then we squared it. Squared deviations from the mean. Okay, then what do we do? At that point, we add them all up. So it's the sum of the squared deviations from the mean, and then what do? We look at the next part. That's dividing by 1 over n minus 1. Well, imagine for a second that this minus 1 wasn't here. If we add everything up and then divide by the total number of individuals that we have, what is that actually doing? That's taking the average. Okay, so if you can read these formulas, you can see that really what we are doing is taking the average of all of the squared deviations from the mean, but then what do we have to do? We have to take the square root of it to undo that squared part. Okay, undo the squaring by taking the square root. Okay, if you can read the mathematics, it's going to become a lot more easy for you to understand how the mathematics is coming. Okay, now let's go ahead and look at a few more principles and properties of these. First of all, this one you remember from the last lecture, standard deviation should only be used with the mean, and it is not resistant to outliers. How does it affect them? Well, it makes it bigger. The more outliers there are, the larger your standard deviation is. Next, your standard deviation is always going to be greater than 0. Okay? If your standard deviation equals 0, this is not true. It's not that all data points are 0, it's that all data points are equal. That's what it means. If every data point is equal, then there is no variation from the mean, and thus our standard deviation is 0. Okay? Any individuals more than one standard deviation away from the mean are going to be considered atypical, or maybe just a little weird. If anybody is considered more than 2 standard deviations away, they're going to be considered outliers, or they'd be super weird, right? And again, this is going to come into play a little bit later on when we start looking at these things called normal distributions. That's coming. So now use the calculator to find S sub x. I will leave that to you. Use your from your one variable stats calculator. I'll leave that to you to go ahead and enter that in. Go and pause the video now and find that value. All right, if you came back and you found it, you would find that S sub x equals about 2.52. And you think, well, wait, our standard deviation is supposed to be 2.33. Some of these one variable stats calculators are actually going to give you 2 standard deviations, and here's the issue. Okay, what we found when we first went through this was dividing by 7. This was dividing by n, not n minus 1. So this would be like the entire population of 14-year-olds. That would be the population standard deviation. But we know this was a random sample, so really we should have used S. And we should have divided by 6, and we should have ended up getting this value, 2.52 centimeters, when you divide by 6 instead of 7. It's a very long, complicated rationale as to why we do this, and it's beyond the scope of our course. Okay, but we divide by n minus 1 because of this thing called degrees of freedom, which we'll eliminate a little bit later on. But the idea here is that it's making a more conservative estimate because you are working with a sample and not the population. Okay? Now, let's go ahead and try and adjust for this. First of all, let's go ahead and jot down what the formula is if we are indeed looking at an entire population. The formula is the square root of 1 over n, not n minus 1, times sigma of x sub I minus x bar squared. So it's still the same formula, except you're dividing by n rather than n minus 1. Okay? Now, let's go ahead and try to use our intuitive understanding and interpretation of this. We said that if there's anybody within one standard deviation from the mean, that's kind of typical. That's not unusual. So what is one standard deviation from the mean? Well, that's adding or subtracting, and you're finding like an interval. Okay, so let's find an interval of values here. Well, x bar, that was 24 centimeters. That was our typical 14-year-old foot, right? And now we add and subtract from that our standard deviation 2.52. And that's going to give us this interval, 21.48 centimeters on the lower bound and 26.52 centimeters on the upper bound. So I can interpret that in this way. Okay? Any 14-year-old whose foot is less than 21.4 centimeters in length or longer than 26.52 centimeters, they're a little bit weird, right? The typical foot is going to be inside of this range. Typical is inside this range. Atypical would be outside of this range. Now, what if we do 2 standard deviations from the mean? X bar plus or minus 2 S sub x. Well, that's going to be 24 plus or minus 2 times 2.52, and that's going to give me this interval from 18.96 centimeters all the way to 29.04 centimeters. And what we would say is kind of the same thing. Any 14-year-old whose foot is shorter than 18.96 centimeters or longer than 29.04 centimeters are going to be super weird. In fact, that is our exact outlier rule that we talked about in our last lecture. So, do we have any outliers? Do we have any individuals whose feet are less than 19 centimeters? No. And we don't have any individuals whose feet are longer than 28 centimeters. So we have no outliers in this case, but standard deviation gives us that barometer of weirdness. It gives us an interval of what we should typically expect to see. If we happen to see an individual that falls outside of that expectation, we're like, whoa, 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 that person's a little bit weird. All right, so let's go ahead and wrap up with the last little bits of reminders from last time. What measures center and spread to use when, skewed and outliers, because we know these the standard deviation is going to be influenced heavily by outliers. This is when you want to use your median and IQR. And then for any symmetrical distributions, that's when it's more appropriate to use mean and standard deviation. Okay? Remember that the summary statistics that you've been working with the last couple of days, they're generally not enough on their own to describe data. The graph that you draw is going to really paint the whole picture, and that's going to give you all of the shape, unusual, center, and spread. Okay? Use these tools to really address your unusuals, your center, and your spread, but use your picture to address the shape. Thanks very much for watching. I will see you guys next time.